So the title is in the form of a question. I will basically recap what is well known about general covariance. I will then say what I mean about discrete settings, and then skim through possible meanings of the notion of a natively discrete notion of covariance. It's not your traditional talk where I come here and I throw a result at you. The fact is that this is a workshop, but it is also the kick-off of the QISS project, and so it's the right time to ask ourselves questions. It's also been a dream for me to gather the quantum computing and the quantum gravity communities together, and so I don't want to waste my time telling you stuff that I already know. Rather, I would like to take the benefit of having you here. So I really do want to tap into your collective knowledge, but also I want to get through my main points, and so maybe we can postpone some of that. Okay. So, okay. So what do we know what is general covariance in classical, usual GR? So it's this idea that the naming of events, and in particular, usually you would name events in your space-time through a coordinate system, does not matter to what really happens to physical laws. Okay. And the way it is implemented usually is by saying that the physical laws should be expressed as tensors, and when you transform your tensor, when you change your coordinates, you do this. So you have your contravariant indices that transform that way, and your covariant indices that transform that way, and so your tensor should transform according to the same formula. But okay, once it's transformed, it should keep the same form. And what does it mean to keep the same form? It means basically that once you've done your transformation, you can reabsorb the changes inside the physical fields. So it's like it's the same law, but the physical fields' values have changed. Right. This covariance is much simpler when we are talking about a tensor which is just a scalar, because a scalar, if you apply your transformation laws, it just remains the same. It's just invariant. So if you base your physics, for instance, on a variational principle, so on if you use a scalar as an action, as a figure of merit for which are the right space-time solutions, then the thing is immediately covariant. Okay. Good. Now, there are various notions around that are not that may have a similar flavor, but they are not exactly the same as general covariance. So one of these things is the general principle of relativity, which says that physical laws you should be able to express them in any referential frame, including non-uniform referential frames. Okay, and that idea that I could be an observer that is accelerated and have the same physical laws. Actually, you could have done it with a strict subclass of diffeomorphisms. You don't need the full changes of coordinates to do that. For instance, here you just do a lower. So you have this accelerated observer, but you just do Lorentz boosts that are inhomogeneous in the sense that you boost differently this region of space from this region of space, and you will manage to straighten up your accelerated observer. Okay, so I mean that this principle of relativity is actually, I mean, covariance is stronger than that. Covariance is really saying that the only thing that matters is the physical events and their interrelations.
Sorry, can I ask usually what people mean by that last statement is background independence, not covariance.
Okay, so background independence. Let me go there in 2 slides. Okay. So so covariance is this idea that, okay, I can change coordinates. But then, actually, any physical theory can be made covariant at a certain price, at the price of adding a field, which is the metric field. So let's have a very toyish theory of some particles going at the speed of light. And so this particle is there and saying, oh, I'm going to get there. I'm going to get to the finish line in 2 seconds because I'm going at speed 1, and so I'll be there in 2 seconds. Okay. And now suddenly I want to do a change of coordinates, and I suddenly shrink space that way. And what used to be 2 steps away in the X frame becomes just 1 step away in the X bar frame. So I can do that, but then I need to add a field that is basically a speed limit. So this particle still thinks the same. Oh, I'm going at speed 1 again. But actually, well, not really. It hits this limitation panel, which tells it that the speed of light is reduced here. This is a light cone. And so it will only get to the finish line. Well, it will get to the finish line in 2 seconds, actually, even in that system of coordinates. So this would be this is a little computation showing that this is a light ray now with that G bar metric. Okay. So covariance does not imply that you have Kerr space. That's not what it says. So, so what does? Well, there is this notion of background independence. Background independence says physics laws should not assume a fixed space-time geometry. We shouldn't assume flat space. Instead, physics laws should predict the geometry. Okay, but how? Well, background independence doesn't tell you how. It just tells you that they should. And if you want to know how to predict the evolution of the metric, you need covariance back in the pitch. Now, there is this other notion, the principle of equivalence, which is something that we experience. So you can be you can be in a closed room, feeling gravity, and be optimistic about life, and believe that you are exploring space, accelerating, and that you will soon reach the speed of light. Or you could be pessimistic and think that you're just stuck in a lift. Okay, and the actual physical experience that we'll have will be the same, because the fictitious force that you feel from accelerating is the same as a gravity force. Okay, right. So this principle of equivalence, what it tells you is that, well, actually, gravity is can precisely be encoded in this metric field here that you needed to add in order to obtain covariance. And moreover, gravity, is sourced by mass. And so these 2 observations lead you to the idea that mass is going to curve the metric, and it's going to curve space. Okay. So, okay, but the real point I want to make here is that even though covariance does not entail Kerr space, what it does do is that it pinpoints and singles out curvature as the physical quantity that you need in order to evolve your metric field. And roughly the idea is this, that if I find myself sitting at this point, well, okay, the situation is a bit strange. Maybe coordinate 1 here is really at physical distance 3, and in space, coordinate 1 will be at physical distance -2, taking these conventions. Okay, so I don't really like this frame of reference, so we'll do a change of coordinates to try and normalize things a little bit better. And so I managed to get in this new frame of reference that this distance is B1, okay? But I didn't manage to make these distances 1. And so, and this is curvature. And curvature is the thing that resists covariance. And so covariance will lead you to think that if you want to govern the evolution of your metric, then you need to look at curvature, and you need to write an equation about curvature. It could be just flatness, or it could be sourced by the mass, or using the curvature as an action, as we do in GR. Okay. So physics laws and physics symmetries. Physics symmetries, they prescribe physics laws. They justify them. You get some physics laws, then they lead to predictions about observations, and they may be contradicted, etc. But what I mean is the role of physics symmetries is to guide you towards engineering, towards proposing your physics laws. And background independence, although it tells you that you should have a curve space, does not really prescribe a way of evolving the metric, and it's covariance that does that. Okay, and the thing that my feeling is that this story that I've been telling you about, that I've been replaying about general relativity, is kind of lacking in quantum gravity. We don't really have this discrete covariance notion that would be able to guide us into prescribing an evolution for quantum gravity. And so this is my motivation. Right. So what do I mean by discrete? Things will be a little vague here. I'll be really skimming through different concepts of discrete covariance. So I won't really go into a precise setting, but the kind of things that will be suggested by my drawings will be things like Arrighi calculus, where you triangulate space-time, but your lengths are still real numbers. Okay? And so the idea is that a solution in Arrighi calculus is a kind of discretization of a continuous solution. And if your typical scale here is epsilon, then basically you have a finite difference scheme that should approximate GR up to an error of epsilon square. Although this actually is very hard to prove, but that's the suspicion. The things that I personally like better are just networks that really are dual to simplicial complexes. So the graph that is dual to a simplicial complex, and just fixing the length to be 1 in a space-like slice, and maybe we could imagine also having light-like edges that are 0, or time-like that are 1. Okay. And evolution of these. And okay, these were space-time, but if we just focus on space, then in loop quantum gravity we have spin networks, and spin networks you can also view them as the dual graphs of space-like cuts or space or just boundaries, and perhaps the main difference is that the variables are no longer the length, but rather the area whereby you glue your simplices and the volume of the tetrahedron. All of these things are not so different in nature. For instance, if you look at the formula for the volume of a tetrahedron, you will find that the volume is given by the area times the height divided by 3. And so if you have the volume and if you have the area, you know the height of your tetrahedron. And so if you glue them, you know this height, and so you have a bound on the actual distance between this point and this point. Okay, so this is how these two may relate. And moreover, you could prepare coherent states, Gaussian superpositions, and get to Regge. But one thing is sure, which is that Regge is a definite geometry, whereas these things have a bit of a degree of freedom here. I could reshape my triangles and still obtain these distances, and here as well these things are fuzzy. There are not the 6 lengths are specified by these 5 variables. Okay. Right. So discrete covariance. So there are different ideas and really different opinions about it, and people will tell you different things. Now, several people will tell you that in the discrete, this notion is just vacuous. There's nothing to learn. So you switch to the discrete formalism precisely to capture just the physical events and their interrelations. You're already modulo covariance. There is no degree of freedom that you need to remove. If you have different triangulations, it means you are speaking of different physical situations.
I think I have to object to that. In
Okay.
the calculus, that's not quite true. And you have like flat triangulations, and then you can move around vertices. That changes your edge length inside without changing actually the geometry, and you can really see that it's actually gauge symmetry of the action. And so in that case, those are not actually physical degrees of freedom, so you would have to remove them. You can sort of interpret those as a discrete like incarnation of the diffeos, but these are active ones, so they're not passive ones because you don't have any coordinates anymore. So they only act with the dynamic degrees of freedom, but those actually survive. So I don't think it's completely vacuous.
Okay.
But that works on the flat space then.
Let's leave the
Also
discussion
in
for
linearized
question.
No, but okay. I mean, but it depends on the author how you live with that, because some will say, it's great, we have some diffeomorphism there. Some other will tell you, but I mean, okay, perhaps I agree that the flat space situation is the one perhaps ill-defined situation in Regge calculus, but you could also say, look, I have 2 different triangulations. I mean it. It's just like they are just different physical situations. It's just like I have this crystal, and now I just rotate it. Okay. So, right. Okay. Now, so this would be an idea. There is no such notion as a discrete covariance. Okay. Background independence is the only important thing. Okay, but the problem is background independence doesn't prescribe the evolution of the metric in the way covariance did. So then you need to try out different evolutions or different formulas for your actions and just hope that in some continuum and classical limits you will still end up with perhaps the curvature as the action, so the Hilbert-Einstein action, etc. But okay, this is a good point. Actually, a discrete covariance notion should have that. It should be the case that in some continuum and classical limits, you do recover your continuous notion of covariance. Still, again, this is not Einstein's path. I would like to replay his method. I would like a natively discrete notion of diffs, of diffeomorphisms, so that I can get a natively discrete version of covariance, and then I can go to a geodesics frame, and then I can isolate something like curvature as the simplest physical quantity on which to base my evolution. Okay. So a funny idea that you find in the literature is a paper by Kempf. This is the title of the paper. And the basic idea is that actually there's no contradiction between discreteness and continuous functions. In fact, if a function is bandwidth limited, then I can capture it entirely with just a finite number of samples. This is the sampling theorem, and it also works inhomogeneously. I can have many samples here and less samples there. That works. So then you get to this idea that discrete diffeomorphisms may just be about resampling some background continuous metric that you have. Okay? So this is kind of nice, and I thought about it a little bit. It has a big limitation, though, which is that if I want to add a sample to this function, let's say that I want to sample the function here, I actually need to be able to reconstruct the entire function in order to know what its value is here, and then I can place my points. So that means that in this case, there is no such thing as a local generator of discrete diffeomorphism. I cannot just add a point. I need to know my entire universe before I can further sample it, which is not very, very pretty. Okay. So because in the continuum, there is this notion of generators of diffeomorphisms, which are basically just like moving a little bit a space-time point. Okay. And so you would like some kind of discrete equivalent of that, so generators of discrete diffeomorphisms, which would be small changes in your triangulation. So, of course, you will go, a diffeomorphism is a homeomorphism. It doesn't change the nature of the manifold. It doesn't introduce some holes in it. Therefore, and we know that every homeomorphism can be captured by a Pachner move. A Pachner move in 2D, they are just retriangulations like that. Okay? So Pachner moves are obvious candidates for generators of diffs. And in Regge calculus, where your distances are reals, you can also just think about these vertex displacements. Now, people have tried to go along this route. It has problems. So, for instance, it's clear that if I apply a 3-1 move, then I'm losing information little by little, and I'm flattening space-time little by little. And that will introduce some errors. For Regge calculus, typically, maybe you can do vertex displacement, but very small ones. Anyway, you had a margin of error which was in epsilon square, so you can stay within epsilon square. But you cannot really go beyond that, except in the case where you have a flat space. Okay. Still, there is this idea that perhaps is not totally fully explored, and maybe we need to introduce further ingredients like the fuzziness, an idea of polynomial interpretation. But there is this idea that the diffs, the discrete diffs, they may be length preserving, curvature preserving local moves with using some poly interpretations so that the error is kept within epsilon squared.
Do they exist in generics in a generically curved or manifold? Do you have an example where in a generically curved manifold there is any kind of a move that keeps both curvature and distance and distance is the same? Because I think it's an empty set.
Well, I don't think it's an empty set, but
I mean, when you do these Pachner moves, and you introduce or remove edges anyway, so actually, sorry, that
Pachner moves. No, so he's not talking about Pachner moves. This is a different idea.
Well, I think the way I understood it is that he considers Pachner moves as being discrete candidates for diffeomorphism. What you're trying to say. So, yeah. But in any case, I mean, because these things have been studied quite a lot, and so this here is quite a difference in the discrete. So, you know, in the continuum, there's this this action of constraints that do both symmetries and evolution. But in this canonic formulation, for instance, for quadratic calculus, these two roles are played by different things. And for instance, these partner moves, they rather take the notion of evolution moves, or like generating time evolution. Whereas like literally symmetries, in the sense of symmetries of your action, those are actually played by these moving around points within a given triangulation by changing the edge length. And that's perfectly fine also in relation to the continuum, because also the continuum, of course, active diffeomorphisms do change metric degrees of freedom, or and so on. And I mean, those you can actually really literally formulate in terms of constraint structures, just as as in the continuum. So the partner moves, as I would not see them as being actually like generators of diffeomorphisms. They actually play a different role in quadratic calculus, at least.
Okay. Well, I took an appointment with you tonight to discuss about it. Okay, so another idea that I want to defend is the idea that, okay, maybe, you know, as I do 3-1 moves, I destroy information. Clearly, this is coarse graining, but perhaps I could restrict to 1-3 moves or other moves that, like stellar subdivisions that are fine graining my space-time. So then this would be like a scale invariance, if you like. In this paper, we've explored this idea already for Lorentz covariance. So we have some quantum walks that simulate the Dirac equation. The Dirac equation is supposed to be Lorentz covariant, and we have this substitution where you substitute a piece of circuit by a light-like rectangular piece of circuit, and that basically implements the Lorentz transform over the space-time where the space-time circuit that runs your Dirac quantum walk. So this was quite successful, and perhaps we could go along that path. Okay. Now, okay, good. So a further idea, and I'll just go quickly now, is that so as you do these refinements, okay, and you could do them in a number of settings, but in particular, you could do them for these quantum circuits that implement quantum walks and quantum field theories. You could try. You could have this idea that, okay, I'm bunching up some regions of space-times one way, but perhaps I could have done it in another way. Okay, and this change of bunching up, this pushing a boundary, would be a discrete diff. So in that sense, I can view each space-time region as a tensor with some legs, okay? And diffs would then be actions over they would be represented as actions over the boundary of the tensor. And this is the kind of ideas that actually come from Robert Okel. Okay. We have one successful example of that. So again, you have a triangulation of space in this case, which implements the Dirac quantum walk. Let's say you go for, well, you just change the metric. You just skew your triangles. Okay, so then you have a different geometry. Say, okay, it's still flat, but follow me. This is a different metric. Now we know how to reabsorb that into the local unitary of the quantum walk here, so that your triangles are back to straight again, but the local evolution is different. So we are able to reflect a change of geometry at the boundary into an action on the tensor. Okay, It's one of the rare examples where we know how to do that. Okay. I'll just mention that there is also this idea that discrete covariance may be a gauge theory where the lapse and shift would be the gauge transformation. Right. Okay, and go to my conclusion. So the point I want to make is that we need discrete covariance. It isolates the simplest physical quantities that then prescribe the evolution. But it's a bit of an elusive notion. The sort of ideas that emerge from skimming through the literature is this idea that perhaps moving boundaries over refinements, you get this idea of acting on the boundaries of these chunks of space-time in a way that is akin to a gauge theory. Okay, another point that perhaps I wanted to ask is whether these notions of quantum reference frames could be handy for discrete covariance. Okay.
So one very good question, Jakub.
So in the continuous limit generators, the diffeomorphisms satisfy the first-class algebra, the hypersurface information algebra. Did you check, what is the fate of the algebra in the discrete cases that you investigated?
I didn't. I think that Philip did, and he is the right person to ask the question. Yes.
I love very much in your theory, but in financial calculus and full theory, like in 3+1, when you have curvature, you don't have any such algebra anymore because are broken. But in like the linearized regime, the symmetry generation algebra, of course.
We disclose.
But we can discuss more later.
So, yes, let's speak here again.